Hello, it's time to move to Module 5, which deals with discrete random variables. In this first part, we're just going to look at a little bit about types of random variables and what a random variable is. A random variable is basically a numeric outcome of an experiment. It's a process by which we put numbers on the outcomes of an experiment. Sometimes those numbers are obvious. If my variable is the roll of one die, then I will simply use the numbers 1, 2, 3, 4, 5, 6 as the outcomes, as the numeric outcomes of that experiment. If I'm talking about flipping a coin, heads or tails, there is no automatic numbering system associated with that variable, but I could make one up. I could say let x equal 1 if you flip a heads and x equals 0 if you don't. That is, if you flip a tails. Random variables are generally classified as one of two types, either discrete or continuous. A discrete variable, and gets the name discrete because the outcomes will be at distinct points, as we'll see in a moment. It usually has a finite number of outcomes, but it could also have what is called a countably infinite set of outcomes. Whereas a continuous random variable will be able to assume any value in some range and therefore has an infinite number of outcomes. Let's look at some more specific examples. Let's start with discrete random variables. Suppose we have a random variable x here that can take on the values 0, 1, 2, 3, and 4. But no other points are allowed. No other outcomes can happen for this variable. This variable is therefore discrete. It can only occur at those distinct outcomes. You can't get a value of 1.73 or 2.67 on this variable. Some simple little examples of discrete variables. The number of coins in your pocket might be 5, 6, 7, but it can't be 6.836. The number of students in your class might be 20, 21, 22, but again, it can't be 22.78. The number of televisions sold daily in an electronics store could be 0, 1, 2, 3, etc. As I said, some discrete variables can actually have an infinite number of outcomes. If the variable could potentially go on and on, for example, the number of people who walk into a store in any given time period. It could go up into possibly the hundreds or thousands, depending on your time period. But again, it would still be a discrete variable, because only whole numbers would be outcomes of this variable. Here we have the variable x as a continuous variable, saying that any value from 0 to 100 is possible, including fractional values. If we can measure a variable precisely enough, we can sometimes think of it as continuous. The time it takes you to drive to school, if we want to measure it in minutes, or get down to even seconds, or possibly tenths of seconds if we had precise measuring, we could think of it as effectively continuous over some range. The time it takes an assembly line process to complete a particular task. So things like time, distance, weight, things that need to be measured in some way and can be measured precisely enough, could be thought of as effectively continuous. Now in this module, Module 5, we're going to talk about discrete random variables, and continuous random variables will be the subject of the next module. A discrete random variable is said to be characterized by its probability distribution. A probability distribution is going to show the values of the random variable and the associated probability of each value. There's a variety of ways to do this. We can use a table to illustrate a probability distribution. In some cases, we can use a graph or an equation. We're going to kind of switch over to functional notation now. We're going to let the symbol f of x stand for the probability function of the variable x. So when I write f of 1, that's equivalent to saying the probability that the variable x equals 1. It's a little bit easier to use functional notation rather than write out lengthy probability statements. As before, as back in the module on probability, probabilities, the f of x's, must be numbers between 0 and 1, and the sum of the f of x's must equal 1. Let's just look at a couple of simple examples of discrete random variables. Let's let x be the roll of one die. Somewhat obviously, the values of x, the values of the outcome of the variable, are the numbers 1, 2, 3, 4, 5, 6. And assuming a fair, well-balanced die, the f of x's would all be a sixth here. In this case, we could actually come up with an equation to represent this. Basically, since there were 6 outcomes to the variable, all equally likely, we simply have an equation that f of x here has to be 1/6 for the x values 1, 2, 3, 4, 5, 6. In general, if we had n outcomes like this that were equally likely, we'd have a probability of 1 over n, or an f of x of 1 over n, for each of the probabilities. This is actually what's referred to as a discrete uniform random variable. Uniform in the sense that all of the probabilities are equal. In an earlier module, we used this discrete random variable, x being the number of TVs sold, 0, 1, 2, 3, at some electronics store, with probabilities 0.1, 0.3, 0.4, and 0.2, which we'll now call our f of x's. Remember, we got those probabilities, the f of x's, by basically calculating relative frequencies. 5 out of 50 days, we had sold 0 TVs, and so forth. Finally, in some cases, we can just draw a graph of the distribution as well. This is just a line diagram showing you the distribution we just looked at. X could be 0, 1, 2, 3. The probability that x was 0, f of 0 was 0.1, f of 1 was 0.3, f of 2 was 0.4, and f of 3 was 0.2. So as I said, we can illustrate a discrete random variable either with a graph or an equation or a table. And that's all we're going to do here in part 1. Next, we're going to take up the question, how do we find the mean, variance, and standard deviation of a discrete random variable?